So we continue with applications of Bernoulli's principle and look at different applications. One of the things that we observe in tubes, if we have an ideal fluid, and as you will remember, we define ideal fluid as a fluid that who has no viscosity. Now, it doesn't happen in reality. All fluids have some viscosity, whether it is small or large in comparison to each other. But this is an ideal situation whereby the viscosity or viscous effects are zero. So you observe here that if there is no viscosity, then if we look at the fluid flowing in pipes, they are at the same level on the top. And so the pressure is maintained. The pressure here, you can see remains the same throughout, and it is supported by the Bernoulli's equation, or it supports that equation. But this is a condition in which the fluid is supposed to be ideal. But in reality, when there is some viscosity there, then the pressure slowly decreases. As the fluid flow covers some distance, then the fluid at the tail end has almost no pressure after a certain distance. That distance can vary from application to application, problem to problem, situation to situation, but it does decrease. And that thing is reflected in this green color, that here if the pressure was at this point, it has decreased a bit. The fluid flow, the pressure is not sufficient enough to support the height of the fluid up to this point. It could push the fluid only up to this place. And similarly here, it's even less than as compared to this, and so. So you can imagine if we travel further, then the pressure will be decreasing. That is why, for example, in opal channels in our agriculture lands, when there is a fluid flow, and the water is provided to the land, then at the tail end they say that the water is not sufficient, and we hear from time to time that the farmers are always complaining about lack of water. Now, one of the main things there is, of course, that the pressure decreases and the flow of water comes to a stop. But there are, of course, other reasons also in that case. But one of these things, that the decrease of pressure, of course, is there. And this happens when there is viscosity. Because when there is viscosity implies internal friction. The particles of the fluid, when they collide with each other, they give rise to friction, and the frictional force is in the opposite direction as compared to the direction of the flow of the fluid in which the fluid is flowing. And when there is frictional forces, some energy is lost due to heating. And where is that energy comes from? This is the important thing, because as we know from the law of energy, from the conservation of energy, that it cannot be created, so it has to be provided from within the system. So equation of continuity, when it applies, the energy cannot come from kinetic energy. So it must be provided from the energy of the fluid, and that to be able to provide energy from the fluid, there is a pressure drop along the tube, and that's what we have observed. We consider here another example, that let's assume that there is fluid, it could be water or whatever, in a certain container, and the level of it, the height of it, is indicated in light blue color. The height is indicated as h. The levels are considered as y2 and y1, and therefore you can see the height is equal to So the water level is Y1 minus Y2, which is denoted by H. Just outside there is a tap. The water is supposed to flow. When they open the valve here or the tap here, then the water is supposed to flow here. And the question is, they want to know that what will be the velocity at this point at the bottom of the tap or the hole at the bottom. And that is the question shown in red color at the bottom. P1 and P2, because we have to equate Bernoulli's equation. So P1 over rho plus half V1 square plus GH has to be equal to P2 over rho plus half V2 square into GH. The two have to be equal, and of course this is with respect to the distance that is there at point 1. So this will be Y1 and this will be Y2. As we open the tap, the flow will start, and just at the start V1 be almost 0. The pressure at point 1 at the above level will be equal to atmospheric pressure, and the pressure at the bottom will also be the same as the atmospheric pressure as the condition of the problem dictate. So with these conditions we can see that this is the Bernoulli's equation. It has to be constant. That's what the equation dictates. And when we substitute the values that I just mentioned as V1 and P1 equal to atmospheric pressure, P2 also atmospheric pressure, so they are the same. When we substitute the cutoff and we have the values as rho into G Y1 equals this, and therefore V2 will turn out to be this value, and when from this we obtain Y1 minus Y2, by the way, has been denoted by H, the height, the difference between the water level, and which results in what we want to know, V2, and that is determined as equal to root 2gh. This is the velocity that we have, and this is known as Torricelli formula found by, first of all, this was determined or observed by an Italian scientist. Incidentally, this turned out to be the same velocity as the particle that is falling from in space from a height h. You will remember that from equations of motion we have that value. The distance, let us say if it is y, is equal to ut plus half g t square, or the same equation when written instead of time we have v1 square minus v2 square is equal to 2gh, something like that, and from that we can obtain this value. And it turns out that since the initial value is 0, anyway, you can see from here it's the same as this. So this is what we obtain. So a container, if we allow fluid to flow out of a container, the velocity at the bottom will be root 2gh.